Just a little bit more on alpha beta power so that you feel comfortable finding out your sample size. So we'll talk about calculating power, using the tool to calculate power, factors impacting power, calculating sample size, and applying this to your midterm project. So this is where we left off at the end of the last lecture. We had population 1, our treatment group, with a mean of 106, and we will actually change that to say the mu for population 1 is 106 because now we're talking about populations and not samples. Our population 0 had mu of 100. Let's call that mu 0, or mu 0 equals 100. We had these spread characteristics with an n of 17, and we used alpha 0.05 in a one-tailed high test, and we found that that t-score associated with alpha was equal to 1.75. So let's orient a little bit to the slide and then figure out how to calculate the cutoff point just so you see what's going on here. So this is the distribution for population 0, our general population. Here is the distribution for population 1, which is our treatment population. In order to, and this is the line that we're trying to figure out. So this is the cutoff point. We know that on our population 0, our null population, we know this is corresponding with 1.75. We have to find out on this other distribution, on this one, what is the t-score associated with this point. And then we can look up the percent of scores that are on either side of it to figure out our power. So the first thing we need to do is just figure out the raw score. So we'll call it the mean associated with alpha. And all we have to do is use our regular old formula for going from z-score to x. In this case, we're going from a t-score to m, and we're going to figure out equals mu 0. We don't need the parenthesis there, and we're going to add to it the t-score associated with alpha times the standard deviation for the distribution of means. And if we run that calculation, we find out that the raw score is 105.25. In other words, the raw score for the group at this cutoff point would be 105.25. That makes sense if we look at where that would fall right here, 105.25, possibly right around there. I hand drew these lines so they are imperfect. So next we have to figure out, okay, now we know 105.25, what t-score would this be on this other distribution, on this distribution? So let's go ahead and find out the t-score. So we're going to call it the t-score, and I'm just going to call it beta because we're using that type 2 error possibility or the beta possibility. And so we just use our normal formula for a t-score, and we're going to take use these two population mu's instead. So we're going to go the mu score for the cutoff point. Let's see, MA is what I wrote it here. I'm just going to write mu A minus the mu score for population 1, and we're going to divide by SM. And if we do that, we discover that we have a t-score on that distribution of minus 0.25. And so that would be the t-score, a quarter of a standard deviation on this second distribution. Now that we have that, we can go to our calculator tool and look up the percent. And it's the same way we used to look up the percentile for z-scores. It's a little bit of a different distribution, so I'll show it to you. And then we'll look at the tool that we use to calculate power also. So you will recall from earlier that we can have this distribution visualized for us. And so this is the equivalent of our distribution from the last slide, with the 106 in the middle now because this is our treatment population. We have the 103 and so forth. We have the 100, and this is just that distribution from the earlier slide corresponding with population 1. And this is just intended to be an arrow. And this is the minus 0.25 that we calculated. These are the degrees of freedom written in here. This is the t-value written in here. We indicated that it was a right-tailed test, and we discovered that the probability of getting a score at this level, that 59% of the scores are going to be higher than this. In other words, power equals 0.59 in this test. And so if we take the 1 minus 0.59, we discover that our beta, or our risk of type 2 error, I'm just going to write the b there, equals 0.41. 41% chance of type 2 error. So that's how that would be done. You're going to find when we look at the actual calculation that this still isn't quite right, because it's not exactly right, but it's close, because we're working with a t-distribution which relies on a sample size. But you want to remember that what we're actually doing is we're predicting for a parameter, and so the distribution is slightly different. So this is just a prediction, not based on a sample. And so that's why we're going to find that when we actually run the power test, we get a slightly different number, but it's close. And so the actual power is slightly higher. So let's take a look at that next power calculator tool. So this is the power tool that we've been using, and just so you can line up to it, I haven't yet put our relevant data in there, but just so you know how to do it, you would determine whether you're using one-tailed or two-tailed, and you can just keep with 4 digits if you want. We would choose T or Z as it fits our data. Note that when we have one sample, we also used it for paired samples t-test, because remember, that's like having one sample. If we're doing an independent samples t-test, we'll choose 2 samples. We'll enter alpha as stipulated. We'll enter the effect, small, medium, or large, and note that if you change effect, it's also going to change the effect size. You can enter it either way and they will change each other. Our effect type, just keep standardized effect size. That's what we're using here because it places it along that Z or T distribution. And then you can enter your N. If it's a 1 sample test, you're just entering 1 N. If it's a 2 sample test, you'll enter both. So this is what our result was, and when I entered all our appropriate data, as you can see here, it says the power, this is pretty straw, it says power equals 0.63. And you'll recall we had something around 0.59. And so it's fairly close, and the difference is because the t-distribution relies on a sample, and this distribution is what we call the NCP, and it relies on, it's looking at a population. So the distribution is a little bit different. When you get your result, you'll see all of these data down here. You'll see this NCP. All that is telling us is it's kind of like the equivalent of the t-score that we would expect from our sample if all of these conditions are met. It's not exactly a t-score though, because a t-score is always depending on a sample, and we're looking at a population parameter. So what if we wanted more power? So first of all, unlimited power isn't a good thing, just like in the real world. We typically go for something around 0.80 for our power. That's a convention. And that's because if you have too much power, you can detect effects or get a significant result, even if there's like very little difference between the two means. And so because those effects defy practical significance, we usually try and have like a moderate level of power. And this power is, of course, to detect a significant result if, in fact, the research hypothesis is true. And so what do we do if we want a little more power? In our study that we just described, we might want to add some to our sample size, maybe have an N equals, 21 or so, something like that. We can check what sample size might be optimal. We could increase alpha. That is, instead of testing at alpha equals 0.05, we could do alpha equals 0.1. That's non-conventional in psychology, but that would be the way. If you were testing at 0.01, you might want to push up to 0.05. You could, what you would want to do when you're predicting effect size, you're basically saying, okay, how strong is my intervention? What kind of an effect do I really expect? So in the real world, you'd want to improve your intervention to increase the predicted effect size. If you're just playing with numbers, then you can just increase the effect size you want to detect. If you are seeking to detect a moderate effect size of 0.5, you could increase it to 0.8. Or that sort of thing. And then reducing the sample variability. This is something else you do in your real world. You try and get a homogeneous sample, meaning like people who are around, if you're using human subjects, people who are around the same age with the same demographic characteristics, and that would be a way to reduce sample variability. So those are some things you could do if you need more power. For your study, in your project, you're going to be finding the appropriate sample size, and it's the same kind of tool, so it looks very similar, so a lot of the directions are going to be similar. Let's see if there are any differences here. Be careful about the sample. A paired samples t-test is really just one sample. And I don't think there's anything else you need. Make note that Cohen's d is the calculation we've been using, so you'll want to keep that the same. That's a standardized calculation. I think that's about all we have. I've put the link here, and I think I've demonstrated this in other places.